So we're going to talk a little bit about writing the equation of a quadratic function given its graph. So we have this graph over here, and kind of the most prominent feature that we can see that we have is this vertex. And we'll actually do this in two different ways, but the easiest way is probably using vertex form, which we know is y equals a times x minus h squared plus k. Where h and k are the vertex of the coordinates of the vertex. Vertex. So let's go over here, and you can see the vertex is 4, 2. So I say y equals a times x minus 4 squared plus 2, because my vertex is 4, 2. Now I have this a. I need to solve for my vertical stretch. And it looks like it's 2 right here because it goes over 1, down 2, or negative 2 actually. But we're going to prove it, okay, because we have this other point. And this other point is 5, 0. And we know that this is x and this is y. Well, in this equation we have an x and a y that we could plug in for, and then that would allow us to solve for a. So I'm going to say 0 equals a times 5 minus 4 squared plus 2. So now I can solve for my a value given that other point there. Okay, so I'm going to go ahead and subtract 2, and that'll give me negative 2 equals a times 5 minus 4 is 1, and 1 squared is 1, and 1 times a is just a. So a equals negative 2. So we just proved it. It looked like it, right? But we proved it. So now we can say, write the equation and say y equals negative 2 times x minus 4 squared plus 2. Now, if they had, now this problem doesn't say anything about writing in standard form or anything like that. So you can just leave that as your answer. Now, let's do something else let's do the same problem in a different way. And we're assuming that this point over here is the other x-intercept. And we can use factored form to find it as well. So looking at this, factored form is y equals a times x minus x1 and x minus x2, where these are the x-intercepts, right? And I know that my x-intercepts are 5 and 3, it looks like, 5 and 3. So then I can say y equals a times x minus 5, x minus 3. And then I can plug in another point. Well, I'm going to use this vertex point up here, 4, 2. And plug that in. So I can say, and remember this is my x and this is my y, so I can say 2 equals a times, and I'm going to plug in that x everywhere there is an x. And when I do that, now I'm going to simplify. 4 minus 5 is negative 1. Not a very nice one. And 4 minus 3 is positive 1. And negative 1 times positive 1 is negative 1a. And I divide both sides by negative 1. And I get negative 2 equals a. So then my equation is going to be, I'm going to plug that in up here and say y equals negative 2 times x minus 5, x minus 3. Now maybe you're saying, but those two equations are different. Well, let's see if we can prove that they're the same by turning them both into standard form. Let's go here. First of all, to turn this into standard form, the first thing I'm going to do is expand that. So I'm going to just leave this distribution out here. And when I know that this equals x minus 4 times x minus 4, which is x squared minus 8x plus 16. If you need to take a minute, pause the video and take a minute and look at that and make sure you believe me. Then I'm going to distribute that all in, and I'm going to get negative 2x squared plus 16x minus 32 plus 2, or y equals negative 2x plus 16x minus 30. Okay, so that's that. I just converted from vertex form to standard form. Now let's see if that holds true for the other one. So I'm going to go negative 2, x minus 5, x minus 3. Now let's convert that to vertex form. So once again, I'm going to leave this distribution until last. I'm going to expand all this out, and I'm going to get x squared minus 8x plus 15. Then I distribute that in, and I'm going to get y equals negative 2x squared plus 16x minus 30. Whoa, will you look at that? So all three of those equations are just different forms of the same equations, which is kind of cool. And they all give you different information, but those two are the same. All right. So hopefully that will help.